Hello friends, I am Dr. Sudhan Sharma from School of Computer and Information Sciences, Indira Gandhi National Open University. And today's session is about vectors, and this session is an introductory session for the vectors. Now, the objectives of this session are about to discuss about the term scalars and vectors. Apart from this, we are going to define the position vector of a point and understand the concept of direction cosines and direction ratios of the vectors. So, vectors are in fact the quantities which are requiring both magnitude and direction. There are two type of quantities. There are scalar quantities and the vector quantities. Scalar quantities are those quantities which can be represented only by a single real number, that is a magnitude. The such quantities are the examples like mass, you can say volume, area, temperature. Such quantities are representing the scalar quantities. But there are quantities wherein we need both magnitude and direction, like velocity, acceleration, force, displacement. Such quantities are vectors. In order to understand the diagram over is given, that say there are 2 points, vector A and vector B. If we want to find the distance, say we want say that there is a distance of 10 meters in between point A and point B, then we are simply emphasizing that the magnitude, that the gap in between the 2 points is 10 meters. But if we say, if we move from point A to point B, we need to cover 10 meters. That means we are specifying the direction that while moving from point A to point B, then we need to cover a distance of 10 meter. So, distance is nothing but a scalar quantity, but the displacement, what is the difference between the distance and displacement is that displacement represents the minimum distance between starting and ending point. So, if we say that there is a closed path, say the person moves from point A to point B and then moves from point B to point A. So, that means the minimum distance between the starting and the ending point is 0, because the person started from A and ended its journey at A only. So, that means there are two components. One is magnitude. If somebody say, again let me give you one more example. Say if somebody asks you that I want to go to some nearby place, say I want to go to Delhi. I want to go to Delhi, or I want to go to Delhi NCR, some city A, and I say that it is 10 kilometers apart, far. So, but I didn't specify the direction. So, if the city say we are having different directions, say east, west, north, south, then and I didn't specify the direction, then the person may go in any direction, may go here, may go here, may go here, may go here. So, that means if the direction is not specified, then the person will not be able to reach the destination. So, in order to reach the destination, we need to specify the direction, that you need to go 10 kilometers in say direction northeast, or say 30-degree northeast. So, direction is very important component. So, that means we are having two type of quantities. One is a vector quantity and other is a scalar quantity. The scalar quantity carries only the magnitude part and distance is the scalar quantity. Whereas, the vector quantities require both magnitude and direction, and the simplest example is displacement. Now, displacement, as I already said, is the minimum distance between the starting point and the ending point, between starting and ending point. So, you can understand an ending point. So, that means you can say that the distance is if we are moving from point A to point B, and the distance is say you can say the maximum gap between the starting and ending point, between starting and ending point and ending point. So, if I move from point A to point B and then from point B to point A, and the say gap is 10 meters, then the distance will be equal to 20 meters. Distance covered will be equal to 20 meters, but the displacement will be equal to 0 meters, because the minimum distance, the person started from A and it ended at A. So, in the closed loop, the minimum distance between the starting and ending point is 0. That is why the displacement is 0. because we are considering the direction also. But in distance, the person moved from point A to point B, covered 10 meter, and from point B to point A again 10 meters, so distance will be 20 meter. So distance represents the maximum gap between the starting and ending point, and displacement represents the minimum gap, and displacement includes the direction, whereas the distance doesn't include the direction. So that's why the distance is a scalar quantity and displacement is a vector quantity. Now, apart from this, you need to understand that these vector quantities are very important in the field of computer science. We are having n number of representations wherein we are including vector databases, vector graphics, and we are having vector machines. So vectors are very important. And in order to understand vectors in more details, we can say that vectors are the quantities which are having both magnitude and direction, whereas scalar are the quantities which are having only magnitude but no direction. So in order to represent direction, in order to represent a vector, say we are having a point A and point B. So vector are represented by a directed arrow. Vector are represented by a directed arrow, and the representation is AB to the arrow and on the top, and this is the directed line segment actually represents the vector. So if we want to understand that how a vector is represented in a plane, let me show you with the help of an example. That say we are having a coordinate axis, say x, y coordinate axes are there, and there is a point, say x1, y1. So we are going to understand the concept of unit vectors or so, but for just for the sake of understanding in the beginning, say I is a unit vector. The unit vector is the vector which is multiplied by some scalar value to represent the full expression in that particular direction. Likewise, if I multiply I by value x, it will be the x times of unit vector I in the direction x. Similarly, if we want to say we are having coordinate axis x and y, and the representation is x1, y1 is a point in the coordinate plane, then the vector representation of OP, that is OP vector, will be x1i plus y1j. So the vector plane is represented by two real numbers, that is x1i plus y1j or xi plus yj, and this is nothing but the component form of a vector. If we are having a vector in three-dimensional space x, y and z, and there is any point say P, then the point x1, y1, z1 in the three-dimensional space will be represented in the component form as x1i, y1j, z1k, x1i plus y1j plus z1k. So this is the component form of the vector in the three-dimensional space. So that means the coordinate system and the vector representation goes hand in hand. The coordinate system representation of a point in Cartesian system can be expressed in the vector form by including the unit vectors, where I, j and k are the unit vectors in the direction x, y and z. So in direction y it should be j, and in direction z it should be k. So I, j and k are the unit vectors in the direction x, y and z, and we are multiplying these unit vectors by some scalar values, and we are getting the multiples of the unit vectors in that particular direction. What I mean to say you will be able to understand as the discussion proceeds. So if A is a vector, say I want to say that, say there are 2 points, point A and point B, then the direction of the vector is say point A to point B, then vector AB will be represented in this format. And say magnitude of this vector is this, that is the distance. Magnitude represents the distance. So, the vector is having, as we had already discussed, that vector is having two components. One is the magnitude and the other is the direction. So, AB is the magnitude of the vector, and the unit vector in the direction of AB is the vector component. So, this is the magnitude, this is the direction. So, this is the unit vector, or this represents the direction, and this represents the magnitude. And this overall component is the vector representation. So, that means the magnitude of vector A, if I say AB vector is equal to A vector, then I am supposed to express that A vector is equal to magnitude of A vector into A unit vector. So, I hope you understand that. Let me repeat that there are two type of entities. There is a scalar component, there is a vector component. The magnitude of the vector represents the scalar component, and the unit vector represents the vector component. The unit vector is multiplied by the scalar component to get the detailed representation of the vector in that particular direction. So, if there are two vectors, then two vectors are said to be equal if they are having the same magnitude and are having the same direction. So, if there is, say, vector A is there, and we are having another vector, vector B. So, both A vector and B vector are equal because they are having same magnitude and are having same direction. But if the magnitude of the vector is, say, null, so you can say that how the magnitude can be null, then the zero magnitude vectors are called null vectors or zero vectors, because I had already said that if the initial point and the terminal point coincides, in the case of displacement, we discussed that the displacement can be 0. If the starting point and ending point are same, then the displacement can be 0. So, the displacement can be a 0 vector or a null vector, because the magnitude can be 0 because the direction is reversed. The direction is reversed. We move from A to B and then from B to A. So, displacement is minimum distance from starting and ending point. So, the actual distance will be 0. Displacement is 0. But the vector whose magnitude is unity is known as unit vector. So, unit vector, as a general, for say the sake of example, we are always having, whenever we are measuring, we are having some unit. Likewise, for the length we are having, say, millimeter, or so meter is the, so that can be millimeter. So, if we are having the unit meter, then that can be multiplied, say, 10 raised to a minus 3 or 10 raised to a minus 2 or 10 raised to a minus 1, or even say 10 raised to power 1 or 10 raised to power 2 or 10 raised to power 3. Then accordingly we specify the units, that millimeter or centimeter or decimeter or kilometer. So, that means the multiplying factor, this multiplying factor is the scalar component, and we are having a unit, that is the meter. So, the vector whose magnitude is unity, that is 1 unit, is called a unit vector. So, I hope you understand what do we mean by magnitude of vector, what is direction of vector, how to represent a vector, when two vectors are said to be equal, what do we mean by a zero vector and a unit vector. Now, let us understand what do we understand by the concept of position vectors and direction cosines. As we had already discussed, say that we are in a coordinate axis, say x, y, we are having, say, point P, and coordinates of point P are x1, y1. So, that means this point P, the direction, say the vector is given by, say, OP vector. Now, vector OP will be represented by x1i plus y1j, where I and j are the unit vectors in the direction of x and y. So, this is x, this point is x1 and this point is y1. So, y1 multiplied by the unit vector j gives you the y component, and x1 multiplied by the unit vector I will give you the x component. So, that is why the total representation of point OP, the vector OP will be given by x1i plus y1j. Similarly, if we are going to have this point in say 3-dimensional space, then say along x-axis we are having unit vector I, along y-axis we are having unit vector j, along z-axis we can have unit vector k. This is the representation of unit vector. Unit vector is represented I cap and vector is represented by a arrow. So, I is the unit vector along x-axis, j is the unit vector along y-axis and k is the unit vector along z-axis. This is the general representation for the unit vectors. So, if point P is there and the coordinates of point P are say x, y, z, then the vector representation of OP vector, which is equal to vector R will be xi plus yj plus zk, xi plus yj plus zk. Now, the question is how to determine the magnitude. Now, in order to determine the magnitude, simply we need to understand the concept of Pythagoras theorem. Let me recall, what is Pythagoras theorem? Pythagoras theorem is hypotenuse square is equal to base square plus height square. So, let us understand how to determine the magnitude. Say we are having, let us begin with the 2-dimensional system. In a 2-dimensional system, x, y, the point P is there and the coordinate are say x1, y1. The vector is OP, which is say vector R. Then vector OP, that is equal to R vector, should be represented by x1i plus y1j. Now, I hope you understood up to this much how we got the vector expression for this point. Now, after this, let us have the projection of point P on x-axis and this is point x, and projection on y-axis, this is y, or this is y1 and this is x1. So, that means this is R, this is x1 and this is y1, this point is y1. So, applying the Pythagoras theorem, hypotenuse square, that is R square, should be equal to base square plus height square. So, that means what is R vector then? R magnitude of R vector then? Square root of x1 square plus y1 square. So, this is the magnitude when we are having the point in a 2-dimensional space. In a 2-dimensional space, in case it is a 3-dimensional space, likewise shown over here, the vector representation of R will be x1i plus y1j plus z1k. So, therefore, the magnitude of R will be equal to square root of x1 square plus y1 square plus z1 square, which is given over here. So, I hope you understood what do we mean by magnitude, how to express a point in 2-dimension or 3-dimension into its vector equivalent, and how to determine the magnitude of the vector from the vector representation of the point in 2-dimensional space or 3-dimensional space. So, again let us extend our discussion, say for the sake of simplicity, let us start with a 2-dimensional system. Let x, y are the coordinates and say point P is there and which is having the coordinates x1 and y1. Now, say x1 point vector R, that is OP vector, is subtending angle say alpha with x axis and beta with say y axis. Then the cosine of alpha, and cosine of beta are actually representing the direction cosines in x axis and y axis. So, why we had taken cosines, why we had not taken sine or tan component? Because we know that this representation perpendicular upon hypotenuse represents sine component, base upon hypotenuse represents cosine components, and perpendicular upon base represents tangent component. So, applying this understanding into this figure for two-dimensional system, this point is x1 and this point is y1, and this gap is r, this is hypotenuse. So, base is this in this triangle, so base is x1 by hypotenuse r will be equal to cos of alpha. So, that is why this is the direction, and x1 represents the x component of the vector OP, x component, direct component of vector OP in the direction of x axis. So, that is why we can get x1 as equal to r cos alpha. So, this represents the direction cosine, because in which direction point P is, the point P in xy coordinate system, the point P is in the direction x1 y1. The vector representation of point P will be given by OP vector is equal to x1i plus y1j. The magnitude of OP vector will be equal to square root of x1 square plus y1 square. And the cosine of alpha, because alpha is the angle subtended by vector OP in the direction of x axis, will be equal to x1 upon r, and r is nothing but magnitude of OP. So, you can say that cos alpha is equal to x upon square root of, or you can say x1 upon square root of x1 square plus y1 square. So, if OP makes an angle of alpha, beta and gamma, likewise shown over here in a three-dimensional system, say with x axis it subtends an angle of alpha, with y axis it subtends an angle of say beta, and with z axis it subtends an angle of say gamma. So, the alpha, beta, gamma are the angles with the positive directions of x, y and z axis. Then the cos alpha, cos beta and cos gamma are the direction cosines of vector OP, and they are usually denoted by the letter L, M and N. L, M and N. So, that means to say that if we are having say three-dimensional system is there, x, y and z, and we are having say any point say P, x1, y1, z1, and O is the origin, and the direct vector is say vector r is equal to OP vector, and the magnitude of OP vector, that is equal to vector r magnitude, will be equal to square root of x1 square plus y1 square plus z1 square, and vector OP will be represented by x1i plus y1j plus z1k, and the cosine, the angles, say this subtends an angle alpha with x axis, beta with say y axis, and gamma with say z axis. Say this subtends an angle gamma with say z axis. Then cos alpha is equal to L, cos beta is equal to M, and cos gamma is equal to N. So, L, M and N are the direction cosines. And there is a very important understanding that cos square alpha plus cos square beta plus cos square gamma is equal to 1, that is L square plus M square plus N square is equal to 1. We will prove this in our subsequent slides. Now, it is already explained that cos alpha is equal to x by r, where r is the magnitude of the vector OP. So, that means cos alpha is equal to x1 by square root of x1 square plus y1 square plus z1 square. Similarly, cos beta will be equal to y upon r, and cos gamma will be equal to z upon r. Now, let us understand one more concept, which is nothing but our direction ratios. Now, we learned that cos alpha is nothing but L, cos beta is nothing but M, and cos gamma is nothing but N. So, that means L is equal to x by r, M is equal to y by r, and z is equal to n by and n is equal to z by r. and n is equal to z by r. So, simplifying these equations, you can say that x is equal to LR, y is equal to MR, and z is equal to NR. And LR, MR and NR are nothing but direction ratios, and they are represented by A, B and C. So, just to simplify that, we are having a vector, and this vector is subtending some angle with x-axis, y-axis and z-axis. So, we are having a vector. For the sake of understanding, say we take a two-dimensional system, OP, xy, coordinates are x1, y1, and this is subtending say angle alpha with x-axis and beta with y-axis. Then cos alpha is equal to L and cos beta is equal to M, and they are the direction cosines. And this is nothing but x by r, and this is nothing but y by r. So, that means x is equal to LR and y is equal to MR, and they are nothing represented by A and B. A and B are the direction ratios, and alpha beta or L and M, they are the direction cosines. So, many times we are not going into the details that in computer graphics we are having the concept of the parallel projection and the perspective projection, wherein we are having the concept of the parametric equation of line, and at that point of time when we are having the parallel projection, then we need to address the concept with the help of the direction ratios and direction cosines. We are not going into those details, but just to make you understand that the concept of direction ratios and direction cosines are very important in the field of computer science. And one of the example for direction ratio and direction cosine is in computer graphics, when we are addressing the problem of parallel projections and perspective projections. So, in order to have better understanding, let's solve some numerical. Now, over here the question is find the magnitude and direction angles of the position vector of the point 1, 2, minus 2. So, point P which is given to us is 1, 2, minus 2. So, if we say it is OP vector, for the sake of understanding, say this is, we are having a three-dimensional system, we are having some point P, and this is x1, y1, z1. So, the vector representation of this point P, that is vector OP, will be given by OP vector will be equal to x1i plus y1j plus z1k. So, this vector will be represented by OP vector will be represented in this case will be 1i cap should be there plus 2j plus minus 2k. So, this is vector r. The magnitude of this vector r, that is magnitude of OP vector, will be given by square root of 1 square plus 2 square plus minus 2 square, which is this, and this turns out to be square root of 1 plus 4 plus 4, that is square root of 9, and that turns out to be 3. So, we got the value of magnitude of r, that is equal to 3. So, this is 3 units is the magnitude of this vector. Then we also understood that we are having the concept of the direction cosines, and we learned that direction cosines are actually the angle subtended by the vector OP along x, y and z axis. So, say we are having alpha as an angle subtended by vector OP along x axis, beta is vector angle subtended by vector OP along y axis, and gamma be the vector subtended by vector OP along z axis. Then cos alpha is equal to L is equal to x by r, and what is value of x? Value of x given is 1, value of y is 2, and value of z is minus 2. So, value of x is 1, so 1, and what is the magnitude of r is 3. So, that is 1 by 3. So, cos alpha is 1 by 3. Similarly, cos beta, that is equal to m, will be equal to y by r. And what is the value of y? Y is 2. So, 2 by 3. So, cos beta is 2 by 3. Similarly, cos gamma is equal to n, and that is equal to z by r, and that is equal to minus 2 by 3. So, we got cos alpha, beta, gamma, and you can always determine the values of alpha, beta, gamma by using the formula cos theta, say is equal to say some value phi, then theta is equal to cos inverse of phi. Then theta is equal to cos inverse of phi, and which we had done over here. Alpha, beta and gamma are cos inverse of 1 by 3, cos inverse of 2 by 3, cos inverse of minus 2 by 3. Minus 2 by 3 should be there, and this turns out to be these values. So, these values are acute and this value is obtuse. So, the vector forms acute angle with x axis and y axis, whereas obtuse angle with the z axis. So, I hope you understood what do we mean by vectors, what do we mean by direction ratios and direction cosines. Now, we are going to prove this important identity, which we had explained also earlier, that L square plus M square plus N square is equal to 1, where L, M, and N are the direction cosines. So, again it is the same thing, say OP is the vector is equal to vector OP, and it is subtending some angle, say with the positive axis, positive part of x, y and z axis, say alpha, and say this is beta, and say this is gamma. Then we already learned that L is equal to cos alpha, L is equal to cos alpha, M is equal to cos beta, and N is equal to cos gamma. So, if OP angle vector OP, that is vector R, subtending angle L, alpha, beta and gamma with the positive direction of x, y and z axis, then L is equal to cos alpha, M is equal to cos beta and N is equal to cos gamma. So, the vector OP, that is vector R, will be given by xi plus yj plus zk. Apart from this, we also learned that cos alpha will be equal to x by r, and cos beta is equal to y by r, and cos gamma is equal to z by r, and cos alpha, cos beta, gamma are L, M and N. So, you can say that by simplifying these equations, you can always rewrite them as x is equal to r cos alpha, y is equal to r cos beta, and z is equal to r cos gamma. So, you can express them in this manner. We also learned that the magnitude of r will be equal to square root of x square plus y square plus z square, and we already found that cos alpha is equal to x by r, cos beta is equal to y by r, and cos gamma is equal to z by r. So, and we need to prove L square plus M square plus N square is equal to 1. And we know that L is equal to cos alpha, M is equal to cos beta, N is equal to cos gamma. So, in order to prove L square plus M square plus N square is equal to 1, let's square and add cos square alpha plus cos square beta plus cos square gamma. So, this, because cos alpha is x by r, so it will be x by r square plus y by r square plus z by r square. So, simplifying, so that means we are writing cos square alpha plus cos square beta plus cos square gamma as x by r square, that is x square by r square, y square by r square, z square by r square. So, that is because cos alpha is L, cos beta is M, cos gamma is N. So, this will be L square plus M square plus N square. Simplifying this expression, that is x square by r square plus y square by r square plus z square by r square. You can always rewrite that r square x square plus y square plus z square, and x square plus y square plus z square is nothing but r square. So, there is r square in the numerator and r square in the denominator, they will cancel out and the answer will be 1. Hence, it is proved that L square plus M square plus N square is nothing but 1, which is an important identity for direction cosines. Now, let's solve one more numerical that finds the magnitude and direction of the position vector p 1, -1 and square root of 2. So, the point p is given to us. So, say it is given by vector OP, which is equal to vector r. So, the magnitude of this will be equal to x square plus y square plus z square. What are x, y and z component? One is x, -1 is y and square root of 2 is z. So, this will be equal to square root of 1 square plus -1 square plus square root of 2 square. This turns out to be square root of 4, that is equal to your 2. Now, you already know that cos alpha is equal to x by r. So, we know r is equal to 2 and x is equal to 1. So, that means cos alpha is equal to 1 by 2 and 1 by 2 is nothing but pi by 3. Similarly, we can get cos beta is equal to y by r, y is nothing but -1. So, -1 and r is equal to 2. So, it turns out to be -1 by 2. Therefore, beta turns out to be 2 pi by 3. Similarly, cos gamma is equal to z by r and z component is square root of 2. So, square root of 2 divided by r and r that is equal to 2. So, this is 1 by square root of 2 because square root of 2 by 2 can be written as square root of 2 by square root of 2 into square root of 2. So, that means it is 1 over square root of 2 and 1 over square root of 2 is nothing but pi by 4. So, the gamma is equal to pi by 4. So, I hope you understand how to solve these numericals. One and final numerical for this session is find the position vector for the point x 0 3. So, you are supposed to find the value of x. So, the point given to us is point is x 0 3. So, the x component is not given to us. So, the vector OP will be equal to square root of x square plus 0 square plus 3 square and the magnitude is given to be 5, which is given over here. So, that means 5 is equal to square root of x square plus 9. So, squaring both the sides, you can always write square root of this is equal to square root of x square plus 9 whole square. That means 25 is equal to x square plus 9. That means you can rearrange that x square is equal to 25 minus 9, that is equal to 16. So, x square is equal to 16, that means x is equal to square root of 16, that is equal to plus minus 4. So, the value of x can be plus minus 4. So, I hope you understood what are vectors, what are scalar components, what do we mean by magnitude and direction of vectors, how to determine the magnitude, what are direction cosines and direction ratios. So, we covered some of the numericals which are very important to understand, and I again advise you to go through these numericals, go through the content given in your self-learning material, watch these sessions and read the content given in your self-learning material in parallel for better understanding of the concepts. Thank you.